Welcome to my Week 8 Everything is the Same demonstration, where today we'll be playing with LEDs, capacitors, and resistors. The first thing we need to do is calculate the diffusion constant for the circuit as shown in the instructions. Here we have a resistor of 330 ohms, a capacitor of 1,000 microfarads, and the diffusion constant is given as the equation 1 over RC. This gives us a diffusion constant of 3.03. Now in electrical circuits, it's a little bit more common to deal with the time constant for an RC circuit, which is simply 1 over the diffusion constant. In this case, it's about 0.33 seconds. Now we go on to calculate the estimated end voltage of the circuit. And on the left here, we see if we start with a large capacitor of 4,700 microfarads and a charge voltage of 9 volts, the charge contained in that capacitor is C times V, or 0.42 coulombs. Then if we form a second capacitor as the parallel combination of the 8 1,000 microfarad capacitors and the 4,700 microfarad capacitor, we end up with a bulk capacitor that has the same amount of charge stored on it, and dividing that charge by the total bulk capacitance, we come up with what should be an estimated 3.33 volts. Now I didn't have any 1,000 microfarad capacitors laying around the house, so I used 2,200 microfarad capacitors. I'll perform the same calculations for that system, and we see that my circuit should have an end voltage of about 1.9 volts. Now let's take a look at the energy at the beginning of the demonstration and the energy in the system at the end of the demonstration. Energy is given for a capacitor by 1/2 of CV squared. So for the first 4,700 microfarad capacitor and 9 volts, we have an energy of 0.19 joules stored in the capacitor. And if we take the bulk capacitance at the end times the voltage that we calculated in the last step, we see that there is only 0.04 joules left in the system at the end. What happened to all of that energy? Well, we don't have just capacitors in the system, of course. We have the resistors as well. And although the charge is conserved, the resistors dissipate some of the energy during the settling period. So at the end, we have 1.9 volts and 0.4 joules stored. Now on to the demonstration. I first discharge the system a little bit, and then hook up a 9-volt battery, let it charge. Now I'm doing this in a dark corner because these LEDs weren't getting very bright. Once I have the capacitor fully charged, I move the lead over, and I can see immediately the closest LEDs to the initial capacitor light up, and then slowly that light diffuses across the rest of the circuit. Let's take a look at what simulation can tell us about how this circuit just behaved for us. For this simulation, I used a common electrical simulator known as SPICE, a simulation program with integrated circuit emphasis. This particular version I use is from Linear Technologies because it's readily available and free. Here we can see I've duplicated the schematic that was implemented on the breadboard. I've got a basic model for a red LED included in there, just a random red LED, not necessarily the one I used. And if I run that simulation for 10 seconds, I see here what the output is. Now at first glance, it looks very much like what Professor Murphy showed in the instructions. We see the red voltage on the main capacitor discharging quickly, then the next capacitor in line charging and discharging. But I've also drawn a line here on the plot at 1.9 volts. And that is what we calculated the end voltage to be, but the simulation tells us that's not where the circuit is going to end up. And in fact, this also matches or comes close to reality. When I take a look at what a multimeter says the voltage at the end of that chain is at the end of about 10 seconds. Why is this? Well, it's because we don't just have the resistors in there dissipating energy, we also are dissipating energy with the LEDs that we have hooked up to it. It takes energy to make light. Here are a couple of plots characteristic of what LEDs do. On the left is a picture of the forward voltage drop necessary to start putting light out of an LED. And on the right, we've got a plot showing pretty much an exponential relationship between forward current and the brightness of the LED. So we have energy being dissipated in the resistors, and we also have energy being dissipated in the LEDs. Let's take a look at what the simulation would tell us if we remove the LEDs from the circuit. Here I've done just that. Run the simulation for about 10 seconds to see what the end voltage is. And as we can see here, the simulation in this case predicts that the end voltage will be 1.9 volts, just as we predicted based on the earlier calculations around conservation of charge. Thank you very much for watching, and I hope you enjoyed Everything Is the Same just as much as I did.